Hello everybody, and welcome to another lecture on this series of lectures about computer architecture. Let's do the third part about digital systems, the summary of where we are to see what we're going to do, how we're going to use this for our lectures, for our further lectures of the computer architecture. So what did I tell you in the last two lectures? Is that we have actually three aspects of our knowledge about informatics. The first thing is that we have the electronics, in fact is how the entire thing is implemented in the real world. And we've seen about CMOS technology and things like this. We know now how to make logic gates. The second thing was that the numbers. Actually, what are we going to implement with our computer? Because what do we want to do with that thing? Well, the idea is to do our calculations. That was basically before it was the idea. Before all this computer gaming came on, it was the idea to do all the scientific calculations. So the thing is then, the third part is the logic that is being used to implement this. It's somewhere the halfway point between these two aspects. We use the Boolean Algebra, and we will see that actually with Boolean Algebra we can come up with any logic function, and then we can implement it with our electronic arrays. So the idea was that with electronics we can make the 6 basic gates, the binary input, 2 input, 1 output operations, and we have also seen that actually you can do this with only NAND gates or NOR gates in CMOS technology. So that is nice. Then we can that we know this. We can just do this with 2 types of gates. Now we can do the logic. We now talk about the Boolean algebra, and we will see actually that this Boolean algebra is based on 3 gates, namely the AND gate, the OR gate, and the NOT gate. And we will then use set theory or group theory, whatever you want to call it, to do the logic. So once again, this is what it's all about. These are the 6 truth tables that we want to implement, and we have already know that with electronics we can just use the NOR and the NAND gate, and we can then do all the others. And then on basis of this we can do everything that we ever want to do. So what we're going to do, we start with set theory, which is a special branch in algebra, or actually in mathematics in general, or a group theory, which is basically the same thing. And we started with our Huntington postulates. Do you remember? Well, let me explain to you then again if you don't. We have the AND operation and OR operation and the NOT operation, and they follow these 7 rules. First of all, they are a closed set, so any operation that you do with 2 elements then results in a third element that is again part of the group or of the set. You also have the commutative law, A plus B, A operation B equals B operation A. It's not specified what is plus or what it means. Actually this is OR, as we know. A dot B equals B dot A. As we know, the dot is the AND operation. We have the associative law, that it doesn't matter in which order you execute the operations. We have the distributive law, that we can actually put things inside brackets or take them outside of the brackets. We know this also from mathematics, but it's a little bit different here in Boolean algebra, but it's basically the same concept. We have an element that exists, that is that then with the operation then results in itself. And for the operation indicated by this plus, we call this element 0, and for the operation with this dot, we call this operation, we just label it with a 1. And finally, there exists an element such that the inverse operated with the inverse element then results in this before mentioned unary, the zeros and these ones. So that is then the Huntington postulates, and then we came that with our 2 operations then is this NOT, which is then the complementary set, the OR, which is then to be in one set or in the other set or in both, and the AND operation, which is in both sets simultaneously. Remember this from our Boolean algebra Huntington postulates. Now the funny thing is, the next step is that to show that any logic function can be made. And we actually learned an algorithm or a method to do this. And engineers like methods, then they don't have to think anymore. So what did we do? Actually, no, I first want to show you this, the useful corollaries of these Huntington postulates are all these that we can use in further calculations. For instance, A and A, now we call them AND, this operation. A and A equals A or A equals A, and so on. All these things we don't have to prove anymore. We have done this in the lectures. If we need them, we can use them. A and 0 equals 0, etc. Very important to remember are the De Morgan laws, which is the complement of the knot of a sum, as we say it. Knot of a sum is the product of knots, and the knot of a product is the sum of knots. As I call it, knot of sum is product of knots, knot of product is sum of knots. And then we sort of make a linguistic approximation by calling this plus, calling it actually a sum, which it isn't, because it's an OR operation. And we call this dot, we call it a product, which it isn't, because it's simply an AND operation. But somehow it sounds nice if we call it the sum of products, which it isn't. It's an OR of ANDs. Remember that. Then we proved all this. But what I want to say is that any logic function can be made. And we use the technique of sum of products and products of sums. So what we do in a sum of products, we take in a truth table where we write down the values, all the output values for all the possible input combinations. We write if it's 0 or 1 or true or false or whatever, false or true. And then what do we do? For the sum of products operation, we just copy all the min terms, which are the associated products, and then use them in a final OR operation. And if you want a product of sums, we take all this, what is called the max terms, which are sums, and then take them in the final product, as you remember. Just to give you a small example, imagine we have this truth table given here on the left, truth table function f depending on 3 inputs a, b, and c, and imagine it has these truth table, these values 0 and 1 for these input combinations. Then for the sum of products, we just copy all the min terms that have a 1 in the line of the truth table. So in this case it is this one is 1, this one is 1, this one is 1, and this one is 1. So we copy these 3 min terms in our final sum. As you can see here, these are sums. All these are sums, meaning ORs, of products, meaning ANDs. And the same we can do. If there's a 0, we take the max term, and then at the end we take this sum, product of sums, which then completely and fully implements the truth table, the logic function f. It doesn't mean that this is the easiest way, the simplest way, but for sure it will result in an answer. Then we went on and said, well, you know what? I want to simplify it maybe if I can. So then we use Kernel maps. So what is a Kernel map? Let me take you an example. Imagine that we had this sum of products and we had this combination. Well, with our Huntington postulate and these corollaries, which I showed you just a couple of minutes ago, we can put this put this A, for instance, A and not A, put them in brackets, as we've seen in this distributive law. Then this A or not A, remember the corollaries, this is equal to 1, which is equal to true. So we can put it, actually you can write it, and then at the end you can see this is much simpler. We can simplify the function. So this function can be simplified to this. But I wanted a more graphical method than just all the time thinking about my Huntington postulates and my corollaries. What we're going to do, we write a Kernel map. So the Kernel map, once again, let's see, there's an example here, function. We have a logic function here, a truth table, and what we are writing down, we write all these 0s and 1 in a table in such a way that between 2 adjacent cells there is only one of the input terms different. For instance, between this one and this one, They both have C, they both have not B, but this one has A and this one has not A. So between two adjacent cells there's only one input variable differing. And then we write them down here. And then we can, for instance, see here there are two ones in a sum of products. There are two ones, which is in this case represented by A and B and C, or A and not B and not C. And as you can see from this, the B term can be eliminated. Namely in such a way with our postulates that we can eliminate the B. And looking back at this, at the table, we see, oh, because the B had and also not B were there, this is the one that was different here. Okay, so I can eliminate my B from my expression. That's nice. Graphically, I can simplify my term, my final expression sum of products. So in this case, there were three such pairs. And remember how we did this with Kernel Maps. This expression, which was the sum of products, the full unsimplified sum of products. With the Kernel Map, we can simplify it to this. And then, of course, also the electronics will get simpler. Then we did this also on an electronic level, which I'm not going to repeat to you because I don't want to repeat all the lectures. But I want to give you now a challenge, because the question that I asked you just a moment ago is, so any logic function can be made from any of those gates, specifically from the AND, OR and NOT gates, or when we do it in electronics, specifically from any combination of NAND and NOR gates. Now the question is, of course, is any math expression, can it be expressed as a logic function like from this postulate? Well, the answer is actually yes. So I'll give you an example. For instance, that's what we wanted to do to make the circle fully complete. That's what we wanted to do. I put here an image. Now imagine that I want to do a summation of 2 bits. I want to have some kind of logic circuit that comes in with A and B, and out comes the sum, I cannot even write so nice, the sum of A and B, and maybe if there's an overflow, which we call in informatics, we call a carry. So we have here the multiplication table. This is actually what the computer has memorized. Well, memorizing is not a good word, it's just burned into hardware. I would not call it memorizing. But this is the multiplication table. A, B, the two input terms, A equals 0, B equals 0. The sum is 0, of course. 1 plus 0 is 1. 0 plus 1 is 1. And 1 plus 1 is 0, but with the carry. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. And then the carry, here's the carry, this will be 0, 0, 0, 1. Oh, this one is 0. So we have here two logic functions, A of A and B. So we have a truth table, A, B. So we have here the sum, and we have carry 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, and this is 0, 0, 0, 1. Two logic functions. Well, I told you, any logic function can be expressed in NAND gates and NOR gates, or AND, NOT, and OR gates. Sum of products of sum, blah, 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 but we already know the answer. This one is an XOR, exclusive OR, and this one, of course, is an AND. So this circuit that we have here, when we want to make a summing thing, it just goes A goes to, how did we do this? I think it was like this. This is XOR. Oh, my mouse is not so nice today. XOR. We have here the sum. And this one here also goes to an AND gate. And this one then goes to carry. So this summing, so now we're in the realm of mathematics. We're doing summing, arithmetic, with integer numbers. The arithmetic has this summing table. The summing table can be translated into a truth table, and a truth table can be translated into hardware. So then we have the full circle. We have the three parts. We have the electronics, we have the logic, and we have the mathematics, and all work together to come up with our computer. So actually there are people that are beginning with the mathematics, there are people that are beginning with the electronics, and there are people that are beginning with the logics. It doesn't matter so much. At the end we are there, we are ready to implement our computer, to build it, and we now start building, and we will see get emergent properties. So see you in the next lecture.